All right, so today we're going to finish up on conditionals. As part of that, we'll go ahead and do a couple of exercises here that would be very similar to what you're doing right now in your hacks and what you did in your labs last week. I do want to bring your attention to that we are online, so if you have any questions, go ahead and post to Piazza or to the YouTube chat here. Otherwise, let's make sure that the audio is working. Yep, good. All right, so to review where we left off last time, we did a bunch of if, else if statements and stuff like that, and then also conditionals. But we also covered some pitfalls, right? You can't use you can't use a range of values. You have to split that up using a conditional, or using a conjunction here. This is logical and. Likewise, with the second pitfall that we looked at, if you use the assignment operator as your equality operator, you're going to get the wrong results, because what this is doing is this is saying put 10 into the variable a, and well, what truth value does 10 have? Every non-zero value is going to be true, so this evaluates to true no matter what. If you had set it equal to 0, well then that would be false. Remember, 0 is always false. Anything else is always true. You can bring in that std bool, that standard Boolean library, to use the keywords true and false and stuff like that, but it doesn't change the fact that under the hood, everything is still represented as an integer, as a number. Okay? Here's another pitfall. So what happens when you execute this code? If a equals 10, so we fixed our issue in the second pitfall here. We're using equals to test for equality. Print a is equal to 10, right? Let's go ahead and run it. So GCC demo, right? And no problems, right? So let's go ahead and run that again. And what's going to happen? Is a 10 in this code? No, 9. So should it print out a is 10? Nope, but it does. Why? Squint really hard here. What's the issue? There's an extra semicolon right here. Right? So what's going on here? If a is equal to 10, then do what? Well, what's between the parenthesis and the semicolon? Nothing. Do nothing. Right? If a is equal to 10, do nothing. Then move on with the rest of the code. The rest of the code being this block right here. So regardless of the value of a, you end up printing out this error, this message that says that a is 10. Let's go ahead and do our trick again. GCC demo.c. What was that flag that I was using all last week to tell the wall flag, the W all flag, the warnings, turn them all on. And now what do I get? This nice message that says, did you really mean to do that, right? This if is bound to nothing. In fact, that's what it says. If clause does not guard, right, in different language. It's saying that this if condition is not attached to any body, right? You're literally saying, if a is equal to 10, do nothing. Did you really mean to do that? It doesn't look like you meant to do that because you have this opening curly bracket right here, right? But the latter is misleadingly indented as if it were guarded by the if statement, as if it were attached to the if statement. Yeah?
So when you're writing like an if statement like that, you want to put like, if you want to say if or this is true, like how many ors can you have? You have
as many as you want. Or a is equal to 1, or a is equal to 4, or a, hopefully you have some other pattern here, but 8 or something like that, right? Now, of course, this is going to be misleading because it's not the correct message here, but you can string them all along as much as you want.
Okay.
Something happens though, right? So that something happens. So again, the issue here is that you've bound it to no statement here. Something does happen there, right? And it's called short circuiting. In fact, did we talk about short circuiting? Nope. Okay, good. So let me bring this over here. So consider the following statement, right? We'll get to exercises here in a bit, but consider the following logical statement A and B, right? Suppose that A evaluates to true, or sorry, to false. Does it matter what B is? So remember that this is the logical conjunction, the and it's only true if both of them are true. A has to be true and B has to be true. So if the first one is false, Does it matter what this one is? Nope. It could be true, it could be false, it doesn't matter, the entire statement is false, right? No, the first one being false makes the entire statement false, right? Regardless of the second operand. So what happens is something called short-circuiting. The code will skip the second statement entirely. It doesn't even look at it, right? If it turns out to be false and it sees a logical and there, it doesn't even bother looking at the rest of it. So now let's go back to your question over here. If A is 10, or A is 1, or A is 4, or A is 8, right? It's going to go from a left to right manner here, and it's going to start evaluating these things. If A is 10, that's true. These are logical or statements. So what happens? Does it look at the rest of these statements at all? If the first one happens to be true? No. And that's going to be short-circuiting on the other side. So again, consider the following, right? Consider A or B. There we go. Let me go ahead and unindent that. Right? If A is true, does it matter what B is? Again, no. The first one being true makes the entire statement true. Now, if the first one were false, then of course we would have to go to the second one. Just like with the AND operator over here, if the first one were true, we still have to go to the second one to see if the entire statement is true. This is called short-circuiting. So you're all engineers. You may or may not have had any electrical engineering yet, but what is a short circuit? It's a bad, right? So what is a circuit? First of all, you go from a power source to a light bulb and then back. Why? Because energy circulates, right? I'm not an electrical engineer, so if I mix up these terminologies or anything like that, then please forgive me. But anyway, what happens if you make a connection from this end over to this end, skipping, short-circuiting that light bulb? What happens? And it circulates, right? But it circulates on the shorter circuit. Why? Least resistance, exactly. All energy wants to go to the path of least resistance. So your light bulb ends up not lighting, and if you have the short circuit, and now it's, what, does it increase your amps on a shorter circuit? Yeah, so then it could blow out the circuit or something like that if it shorts out, right? Or if you've got a capacitor and you start working on something, you definitely, I had to replace a microwave this last weekend. So I wasn't in that part of the microwave, but I have been in that part of the microwave before. You've got this capacitor in a microwave. What is the first thing you do after unplugging it, of course? What's the first thing you do to the capacitor? You discharge it by short-circuiting it, right? So that you don't accidentally get that charge into you, right? In fact, that's what one of our exercises is going to be here today, right? Anyway, a short circuit in code is very, very similar. If it doesn't have to do work, it doesn't do that work. It goes the path of least resistance. So for this example over here, it goes left to right, and the first true one that evaluates to true, it stops and doesn't even bother looking at the rest of it. Now think about why this is. 30, 40, 50 years ago, when you measured computer CPU cycles in seconds, right, even, if you could skip out on a few CPU cycles, you did it, right? And if you could skip out on a few CPU cycles by short-circuiting a logical statement here that ignoring the rest of it is not going to change the truth value of this, then you did it because it saved time. And nowadays, every language still supports this idea of short-circuiting, even though it's no longer a resource issue. It has become familiar. People expect it, and they start writing patterns of code around this expectation of short-circuiting. One of those would be, for example, and we're not going to get to it until we get to pointers or anything like that, but null pointer checks. If A is null and do something with A, right? So I won't talk about what that do something with A is here, but if it's null, it doesn't exist. So if this ends up being true, or sorry, or if this ends up being false, then this entire thing, this over here gets skipped, right? Actually, sorry, and I do want the and. There we go. Sorry, and there we go. All right. So if it ends up being null, it would be dangerous to do something with it because it doesn't exist. So the first one, if that ends up being false, and this is and, it short circuits out this dangerous operation over here entirely. So it's a pattern that we'll take a look at later on when we actually get to pointers. Okay. All right, that's short circuiting. Any questions on that? Otherwise, the only other thing I'll say on it is that it's a popular idiom. Again, 40, 50 years ago, it was done for efficiency. It's still done today because it is familiar and people expect it. It's an idiom. It's a programming idiom. So I've tried to draw parallels between coding and writing as we go along, right? Statements are sentences, blocks of code are paragraphs, you have punctuation, et cetera, et cetera. Well, here we've got another analog to plain old English or natural language. What is an idiom in English?
It's something that has a different meaning to what it is.
It's a metaphorical meaning, a different meaning than its literal meaning. Like, do you have an example?
Piece of cake.
A piece of cake, exactly. What is a piece of cake? It's something that's delicious, right? That's the literal meaning. What is it really meaning, the idiomatic meaning? It's simple, it's easy, right? Now translate that to another language, and they're gonna like, what are you talking about? It's a piece of cake, all right? It's not gonna have any, you have to transliterate it. So if you take it over to another language, they would have their own idioms that would be understood in a cultural context within a language. That's what this is. This is a programming language idiom. It is understood that this language will have short circuiting, so you can write idioms and patterns following that assumption. Okay? You'll see this all over the place. They're idioms. When we get to loops, there will be an idiomatic for loop. For I equals 0, I is less than n, I plus plus. That is the idiomatic for loop. Right? You know that you're iterating over something. Okay? All right. So one other thing that I'll say before we get onto these exercises that we've already taken a look at plenty of times here is linting. Right? So code might be syntactically correct. It'll compile, right? But it may still have errors, bugs. Right? Lint is pieces of code that may look suspicious, but they're not necessarily bugs. They're not something that necessarily will lead to an error or will necessarily lead to the wrong computations. But still, it's something that doesn't look good, or it looks like maybe this is something that you need to take a closer look at, just like lint on your clothes. You can have clean clothes, right? They come out of the dryer, but they still have lint on them. So what do you do with your clothes when you've got lint on them? You take a lint brush or a lint roller and you take it off, right? That doesn't mean that your clothes weren't clean, right? It doesn't mean that people are going to laugh at you and point at you, ha, you've got lint all over you, right? It just means that you probably want to take a second look at that, right, before you go in for that job interview or whatever, right? Linters in code are exactly kind of like that, right? It's a static analysis tool. Static analysis refers to analyzing code before it gets compiled. There's also dynamic analysis, which looks at code after it gets compiled as it's running. We'll take a look at some dynamic analysis tools later on, the most common being debuggers. But this is a static analysis tool that looks at your code before it even compiles, or as it's compiling. And it usually issues warnings for potential errors, not necessarily something that is wrong, but this is probably something that is wrong. You need to take a closer look at this, right? Again, it's an analysis tool that looks at the source code, and there are plenty of others besides GCC. If you want to, we can take a look at the handout that I put up. I don't know how many of them are available, but actually, let's just do it. I'll show you the document here. If you go to the GitHub repo for this course and go under Documents, there is a troubleshooting guide for C. So, test, right? That's the first step to any troubleshooting. You have to come up with some unit tests. We'll get into more formal unit testing frameworks as we get along. But in your lab this Friday, we provide you an informal unit testing framework. You have to write some logic to determine if the year is a leap year or not. All right? And then we provide you a bunch of lines of code that tests, was 2000 a leap year or not? Was 2001 a leap year or not, et cetera, right? You write code to test other code, right? That's what unit testing is. And so that's always your first go-to. Second one is using a linter. With GCC, always use the WAL flag, the wall flag, right? You can use other static analyzers. For example, Clang is another, it's actually a front-end LLVM compiler. Don't worry about the details of that. I even forget what LLVM stands for. Anyway, it can be used as a similar linting static analysis tool. Otherwise, you can use the scan build that provides an even deeper analysis of your code. Facebook has put out a code analyzer called Infer. You can download that and install it, and if you want to, I wouldn't recommend going that far though. But in the future, if you really want to put your code through the rigors, right? These kind of simple programs that you're going to be writing, especially at the beginning of this class, you don't need any of these heavy-handed tools to look in and find bugs in your program. But if you do have a much more complex code base, thousands and thousands of source files, these tools can work wonders. They can find hundreds of potential errors and bugs before they become actual runtime catastrophes. And then we've got dynamic analyzers like Valgrind and GDB that we'll get to later on in the course. But otherwise, this is a good troubleshooting guide that's available on the course GitHub page. It's always just, for now, always just use the wall flag. Turn it on, listen to the errors, and make sure that you're taking care of those errors. On your hacks, you are graded based on the errors that are still there. We turn on all the flags when we run it through the grader. If there are still warnings there, like unused variables or dead code or whatever else, you need to take care of those things. Those are graded under the rubric under design. If you still have leftover warnings, that's at least a point there on every hack. So keep that in mind. All right. Any questions on linters or conditionals? Then let's do an exercise. This first one is going to be pretty simple. In fact, we've done parts of it before already. Let's go ahead and write a program to compute roots, quadratic roots using the quadratic equation, and deal with any bad inputs. So first of all, we're also going to use this as an opportunity to get more practice using command line arguments. According to the TAs, there were some folks that were still struggling with command line arguments versus interactive arguments, using scanf versus using the command line arguments. Let's go ahead and use command line arguments here. Instead of prompting the user for input, we're going to expect that the coefficients of a quadratic equation, A, B, and C, are all provided as command line arguments. First of all, do we need a review on quadratic roots? Yes? No? Okay, good. All right, then let's go over here to my coding environment. And instead of, I'll copy demo into quadratic.c. There we go. And I will open that up for editing instead, okay? So, if I'm going to be reading in command line arguments, A, B, and C, I should document that. All of your code needs at least author and purpose documentation. What I mean by that is above your main, at least for the until we get to functions, this is the minimum amount of documentation that we're looking for. Let's document what this program is all about. This program reads in 3 coefficients, A, B, and C, of a quadratic formula, and computes and outputs the roots. Right? Author, me, and date. What is today? 7? There we go. Right? That's the bare minimum. Right? If that's not there, you don't get your points for documentation. Okay? All right, so if we're going to read these in as command line arguments, in fact, we should write that, of a quadratic formula as command line arguments, and computes blah, 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 blah. Right? So, how many command line arguments am I going to expect here? A, B, and C. Or, sorry, C. Right? Is that it? And the first one is always the executable file name. So, I need to check for 4 command line arguments. If there are not 4 command line arguments, argc is not equal to 4, then that's an error. You didn't give me enough information. There's no way that I can actually process this input. So we're going to echo an error message and then quit. Printf error, provide 3 numbers as coefficients, 3 numerical coefficients. Right. And then we'll exit. How do I exit out of a program prematurely? Exit. Right? And we'll go ahead and exit with an error code of 1, indicating that there was an error, true, right? We'll get to error codes later on when we talk about error handling after functions. A 0 would indicate no error, right? False. No. Was there an error? False. No, there was not, right? But in this case, there was an error because you didn't provide me enough command line arguments, okay? Now, how do I convert those command line arguments to actual numbers? When somebody runs this, they'll run it as a.out 10, 20, and 30. A, B, and C being 10, 20, and 30 respectively. So how do I convert those strings here that somebody is typing out in the command line? How do I convert them to numbers that I can actually use? A, alphanumeric, 2, I. That would be if it's an I is int 4, an integer. So int A is equal to A to I. Now before we go on, let's think about our appropriate types. That's part of design too, right? Now 10, 20, and 30, those are all integers. But are quadratic formulas restricted to integer domains? No, you could have 2.5, 3.75, and then 4.0 or something, right? So instead of integers, how could we change this? What's the other one? Double, right? We could do floats, but floats are just half as much, half the precision, in fact, less than the precision. They're only about 6 decimals of accuracy. Doubles have about 14 to 17 digits of accuracy.
I was talking about the A to F.
Oh, yes. So here, A to I now becomes A to F. Now, where is that first argument? It's an argument vector. And then you provide square brackets to indicate which one. Now, the first one is at 0. That's going to be our executable file name, a.out here. Right? So that's not what we want. We want the second one, which is actually at index 1. Right? Copy, pasta, pasta, copy, pasta, copy, pasta. Right? In general, don't do that. Right? In this one, in this example, it's simple enough that, yeah, you can go ahead and copy that one line. But doing copy pasta leads to spaghetti code. And simple mistakes that you sit there for hours staring until you realize that you copy pasted something and you were supposed to change 3 things, but you only changed 2. Right? That gets you into big trouble. If you've ever heard the term spaghetti code, right, what is spaghetti code? So what is spaghetti? Cooked spaghetti. Right? Can you determine where one noodle starts and the other one and it ends? Nope, it's all mismatched, gobbledygook, complex mess, right? It's unorganized, and you don't want spaghetti code, so don't copy pasta, right? But in this case, it's fine, right? All right, now let's go ahead and compute those roots. Double root 1 is equal to, what's the quadratic formula? Plus minus, but of course I can't do that with 1, so I'll go ahead and do the plus first and then the minus second. Square root of 4b squared minus 4ac, is that correct? Well, is it correct syntax there? Nope, I need those, and then divided by 2 times a. Is that correct? Nope. Numerator needs parentheses. Denominator needs parentheses. Otherwise, the a ends up on the numerator. Okay? Copy pasta, R2, right? And the only difference here is minus. Now let's think about these variable names first of all. A, B, and C in general are terrible variable names if they actually represent something. If A represents the number of students, and B represents the number of exams, and C represents the number of hacks, right? Then those should be labeled as such. Number of students, number of hacks, number of exams, whatever. But A, B, and C, do they represent anything particular here? No, it's math, right? So math, fine. But what about the roots there, R1 and R2? In the context, it might be absolutely clear that these are roots. R stands for root, right? But is there a better name that I could have chosen for these? More explanatory name.
Spell out the word root.
Oh, okay. I ain't paying by the character here, right? And I'm not getting paid by the character, but root is much better. Right? Why? Because it describes what it is. Right? Now, you could say, well, A is a coefficient, so coefficient A, coefficient B, coefficient C. That's getting too detailed there, right? You understand that from the context that it's A, B, and C. Now, this is an argument that you can go back and forth with if you've partnered up with somebody. By the way, if you have partnered up with somebody and you've not partnered up on Canvas, you need to do so before the due date. Otherwise, you will get graded separately, right? But the vast majority of you have teamed up on Canvas into pairs, so great. But in any case, you can go back and forth with a partner and no, this is a better variable. No, this is a better variable name. You know, settle on something that's sensible. You can argue about it all day long. In fact, there's an old saying that there are only two difficult things in computer science. The first one is cache invalidation, and the second one is naming things, right? So you can argue about it all, go back and forth all day long and never get the job done, or you can just settle on a sensible name, root 1, root 2. Good. Let's print those out. Printf. I'm going to print out the full quadratic equation. So here's my first coefficient, %f, x squared, plus my second coefficient, f, x, plus my third coefficient, which is going to be %f, and then that's the end of it, right? And I'll print out a message here. The roots of that blank, and the line, and then I'll print out A, B, and C, just to make sure that we are reading those in correctly. Right? R, and I'll make it look nice, and I'll go down to the next line. Printf, R1, root 1 is equal to %f and the line, and then the second one I'll put on its own line there, and root 1 and root 2. Actually, I'll leave it like this. There we go. GCC, quadratic. Already something happened. What was it? Even without turning on all the warnings, what is this telling me right here? You have a placeholder on this line. In fact, read it. Line 30, column 24, there's a warning, right? There is a placeholder here, right here, that I never printed anything out with. That's just a warning. Go on as if your day, go on. If you don't care about the warning, so be it. Right? But clearly, we should care about the warning here. Why? I'm not printing out the second root. Right? There's still going to be a problem here. Right? What's that complaining about? Square root. I need the math library. GCC is saying that ain't no function I've ever heard of. Right? Well, I'll tell you about it. I'll link you in with the math library over there, and now you do know about it, and you can compile. When I run this without command line arguments, I'm going to get that error message, and it's going to immediately exit. Error. Please provide, I didn't put a please there, but provide 3 numerical coefficients. Okay, fine. 10, 20, and 30. All right. Oh, what happened? Nan and nan. What was nan again? Not a number. All right, that's weird. 10, 1, and 2, 3. Nope, 1. Nope. I need something large, so I need B to be large. There we go. Oh, that looks like it worked. All right, 1, 10, and 1. Okay. Pull out your calculators, is that correct? Probably. Pull out Wolfram Alpha if you want to. That's probably correct. What was wrong with the other ones, though? Yeah.
How did we link the command line again? I missed it when you put it up there. I was typing, but if we...
What do you mean?
Where did we link the math library?
Oh, sorry. Output. There we go. Terminal. So, back up here. -LM. Link the math library. Right? Generally, you put that at the end. Some compilers will complain if you don't put it at the beginning. can put it both. But I think that for the CS50 IDE and the CSE server, -LM will be just fine. You don't have to worry about the CSE server, the grader anyway. I take care of that. Okay? So, what was happening here? 10, 1, and 1.
Imaginary, right?
Imaginary numbers, right? B squared 1 minus 4AC is going to be 1 minus 10 or something like that, or 40 or something. It's going to be negative. So back to the drawing board. Before I compute those roots, what should I be looking for?
B squared is greater than 4AC.
If
Or equal to it.
B squared is greater than 4AC, then is that okay or is that bad?
If B squared is greater than or equal to.
Great. Oh, what about equal to? Equal to is fine. You get, what's the square root of 0? 0. That's fine, right? That's defined. But if B squared is greater than this thing, so this thing minus this thing, that'll be good. That'll be positive, right? So it's only when it is less do I get a negative value, right? Oops. Less. Come on. There we go. So which kind of error message should I print now? I cannot handle imaginary roots. And then exit. You can exit up there or you can exit down here. Now, should I have put this piece of code, say, right here? No. Why? Yeah, you've done unnecessary work. You've done dangerous work, right? In programming, you look before you leap. At least with C programming, you look before you leap. Am I about to compute imaginary roots? If I'm about to compute imaginary roots, I don't do it. I do something else instead. Let's try that again. I recompiled. There, I can't handle imaginary roots. Okay. Is that the only kind of error that we could have? All right, so what if my coefficient A is 0, 1, and 1? Think about this in terms of math, right? That I've got 0x squared plus x plus 1. Right? Is that a quadratic equation? No, right? That's what? It's a linear equation, right? You know how to solve those, just different algebra. So what we could do is we could check for that. If A is 0, then we could print an error message, and error cannot divide by 0, and then exit on them. But is that all that satisfying? Cannot divide by 0. Well, you can't divide by 0, but you could still solve a linear equation. Yeah, it doesn't tell you anything, right? It doesn't say that, so we could be more descriptive here. A cannot be 0, right? There we go. It tells you now that the first coefficient cannot be 0. But what else could we do? You know how to solve linear equations too, right? How? All right, let's do it then. Or, there's only going to be one root now. Root double root 1 is equal to
Negative B over A.
all right, except that A, B, C. So careful, A is gone now,
yeah.
right? So we've got B, C. So it's actually BX plus C. So C on the other side. And then divide by B. Right? Okay. All right, let's go ahead and try that then. And then printf. Printf. You gave a linear equation which has a solution at x equals %f end the line, and then root 1. So for this, I'm going to go ahead and get rid of it initially at least. There's a trick there. I'm going to ask you how I did it in a second here. So you can't divide by 0, fine, right? You gave a linear equation which has a solution at -1. But it went on and did the rest of it anyway. So how could I fix that?
You just exit right there.
Okay, I could exit with no error code, 0. Everything was fine, right? You just gave me a linear equation instead. What's an alternative? False. and then all of this stuff. Right? Except now I have to go in, tab over, tab over, tab over, tab over, or A style, quadratic, and it does it for me. Okay?
Is there a better way? Which way is better? Exiting in the if statement or putting else?
Good question. I'd say that something like this. You don't want to rely on exit codes to dictate the control flow of your program. This is a little bit better, but these are such simple programs that it's 6 of one, half a dozen of another.
Formatting is more or less the difference.
Formatting, but also the design principle of relying on exit. You really only ever want to exit in main. If you were calling a library function, that library function should never exit. Instead, when we get to error handling, it should return an error code, and then it's your responsibility to decide what to do with that error code.
And what's the difference between return 0 and exit 0?
In the context of main, nothing. One is a function, one is part of the language. Right. Right. Let's go ahead and try this out again. Recompile it and run it. You gave a linear equation which has a solution at that. Is that the solution? Yes, it is. Pretty sure. Okay. By the way, what trick did I do up here? I highlighted an entire block and then comment, uncomment, comment, uncomment. Right. Control, or if you're Mac, command and then /. If you are Windows, it's standard in any IDE to do control and then /. Right? Okay. I'll go ahead and leave that in there. I could probably go ahead and combine all of these into one big giant if, else. Right? Can you think of any other problems here?
What if you put in letters?
Yeah, hello. What did it interpret it as? 0, right? What else? So that's a problem. Is there another mathematically based problem? You could still divide by 0 if A is 0 and B is 0. For example, A is 0, B is 0, and then we have 1. Inf, negative inf, is that correct? No, what would that correspond to? So 0x squared, that goes away. 0x, that goes away. Plus c being 1 here, is equal to 0. Has anybody ever taken a math class in which you've proven that 1 is equal to 0? That's a classic bad operations proof or poof, right? That tries to show that 1 is equal to 0, and it shows you bad proof techniques, right? But is 1 equal to 0? No, that's a contradiction. So you could go ahead and take care of that. I'll leave that as an exercise, though. But what do we do about hello, right? Well, we'd have to start reading some documentation, and we'd have to bring in some other tools to bear to see, is that thing that was provided, is it actually a numeric value? If not, then we can handle that differently. We can make it a hell of a lot more complicated than it is right now, but don't worry about it. You will have to do rudimentary error checking starting in hack 3, but not in hack 2 this week. Right? It's good if you do, but like if you the degrees are on the Earth, if they're what is it, greater than positive 90, less than negative 90, or out of the bounds of negative 180 to positive 180, we're not going to throw those at you this week, but we'll start throwing bad ranges at you next week. Okay. All right, that's good enough for now for that one. Yeah.
Is there a way to detect the value of the ASCII input?
There is. For example, if I have char initial is equal to C, right? That's already a value, right? Capital A is going to be 65, so C is going to be 67. If I printed it out as an integer, it is going to print 67 there, right? So you can use them interchangeably. Single characters you can use interchangeably. strings, no. You'd have to go in and treat it like an array, but we're not there yet. You'd have to go in and get the first one and say, well, this has an ASCII value of 67, right? But there are tools that will help you do stuff like that. For example, there's is numeric initial. That'll end up returning false. Is alpha, right? That'll end up returning true because it is an alphabetic character. Is upper, it is an upper case, but it is not a lower case. And those are all tools that you can use later on when we get to strings. Right? Not necessary yet, though. Say what?
Is there a way to check like exclamation or?
Is punct.
characters?
P-U-N-C-T. Is punctuation, yep. Or you could always go to the ASCII text table and find exactly what you're looking for and then write your own if there's not something like that already. Right. Okay. I'll make sure to cut and paste this so that you have this in the notes. Otherwise, let's take a shot at this second program here. So I said that if you short circuit something, you could end up with an electric shock. And I did look this up today to see what the fatal amperage of a circuit is, and it wildly varies, of course, because the voltage doesn't matter that much. It's the actual, amperage that you receive. Charles Dalziel, I found this a while ago. It was just a study on how does an electric shock feel. And so it turns out that for men and women, it's completely different scales for whatever reason, right? And it also depends on whether or not it's direct current, alternating current, or stuff like that. It can vary wildly. So I just chose one of these things, males and direct current. Under that assumption, 0 to 1 milliamperes, is that how you pronounce it? Milliamps, right? 0 to 1, no effect. 1 to 5.2 milliamperes, that's a slight sensation, so you can actually start to feel it. 5.2 to 62 is pain, but you still have voluntary muscle control. So if you're ever, approaching something that you think is a live wire, do you actually grab it? No, why? Because then that will cause your muscles to involuntarily contract, and you now hold on to it, and you're getting the full voltage, right? Instead, what do? If you really want to use your hand, of course you use a tool to do it, but if you just want to test it, you use the back of your hand, because if it is a shock, at least it'll get out of it, right? But at 62 to 70, but within this range, you still have voluntary muscle control. You can still let go. But 62 to 76, and you can get that from a garage door opener wire, trust me. 62 to 76 is going to be a loss of control where you cannot let it go, right? And by continuing to hold on to it, right, then you could have a heart fibrillation, right, eventually. 76 to 90 is severe pain, and then 90 to up to 500 depends on how many seconds you hold on to that amperage, but that can cause death within 3 seconds, right, at the higher end. So what I want to do is write a program that, given milliamperes, determines one of these 6 conditions, right? We're going to read it in as command line argument again. So let's go ahead and copy demo to shock. C. There we go. All right. So same thing as before. What we're going to do is we're going to check for the correct number of command line arguments. Am I expecting 4 though anymore? I'm just expecting 1. So is that correct? Careful. The executable file name is always part of it. So it's always +1, and I'm expecting 2. Okay? Error, provide a milliamp value, right? Numeric. Okay? Otherwise, we'll exit. All right? So double, milliamperes, or whatever, however you pronounce it, or however you spell it, or MA. That could be okay in the context. Right? The context is given by the documentation. So this program reads a how do you spell milliamperes?
You can just say
Millian? Or milliamp? Okay.
AMP.
Milliamps reads a milliamp value from the user. and outputs a danger level for direct current on male subjects using the Charles Dalzell chart. I don't know, chart, whatever it is. Now, why would you want to mention something like that? Because it's just like citing a paper in an English paper, right? Bibliography. If you want to learn more, if you want the user to learn, where did I get this information? I just pulled it out of the air, right? No, I got it from this research paper put out by this guy, blah, blah, blah. You can go ahead and put that in the documentation. It tells you the why. Why did you use this scale? Go ahead and read that paper. Read all about it. It's over there. Right? Question?
I just wondered if the online version of VS Code did the magic doc style comment that looks like it does.
What do you mean?
Using the one I have, like the actual VS Code on my computer, it formats them nicely.
All right. See here. I don't know if I could pull up the website that I did. He's an attorney, okay. Milliamps table, I don't know. There we go. There's a PDF for it. I'll go ahead and copy that link, put it in there, and what am I doing here? I'm using HTML. See here. So this is, I don't do this because, as you said, you probably need a full IDE to get it to work like this, but let's find out. Does it do it? Nope. So in an IDE, probably if you hovered over main, it would format it nicely, right? And it would actually format it as HTML, and if like you could actually click this and get that, download that PDF and stuff like that. These are doc style comments that if you follow them, then you can use these tools, these doc tools, that will compile all of your documentation and then create these nice looking HTML pages for it that are all clickable and cross-referenced and stuff like that. Yeah? Doxygen is one tool just like that. Yep. I think it was born out of Java docs, and then everybody adopted the same thing. You can use code tags here, int a, and it'll format it as code just in a monotype font. You can use things like cross-referencing, so at C quadratic.c, and it would make a link back to that other file, right? You can use this kind of stuff, but we're not going to get it too far into it, right? Because that tool is not supported here. Right? But yeah, Doxygen, is that for PHP? What is that for? What is that for? Okay, all right, yeah. If you get into Python, they have their own world, and so they've got a JEP on doing it completely differently. But these things are pretty universal among most languages. Right. Good question. So MA, milliamps, I like that a little bit better, right? And we'll go ahead and convert that A to I. A to I? Well, not if we're going to allow 5.2, right? So we should allow A to F. argv sub 0, the first one. Remember, that's the command line, or that's the actual executable file name. So what should it be? 1. Right? The first user provided. And if we were doing this, it would be a.out, and it'd say 5.2. That's how many milliamps that we would give it. Okay. Once I've converted it, now I make my checks. Right? 0 to 1, there's no effect. Okay. So if mamps is greater than 0, or mamps is less than 1, printf, no effect. End the line. Is that logic correct? Is that style correct? Okay. You want to just check if it's less than 1? Right? Yeah, what about negatives? So electrical folks, is there such thing as negative amperes? No, there's negative voltage that goes in the other direction, right? But that's a relative term, right? So is there negative amperes?
If it's going the opposite direction.
I mean,
technically
not
consider it negative, but
practically.
it's not.
Okay.
It's like saying it's just direction.
Like, is it sucking the energy out when I touch the wire? Definitely not. So we'll go ahead and say we'll come back to this, right? Negative is probably not correct, all right? So between 0 and 1, right? So 0 is less than or equal to m amps, and this, right? I'm doing a proper, range. If it is equal to 0, or if it's greater than 0 but strictly less than 1, then it'll have no effect. What happens at 1? I intentionally left this ambiguous. What happens at 1? Is there no effect, or is there a slight sensation? Yes. So I should have printed out both. There's no effect, but there is a slight sensation. Okay. Well, this is a problem with specifications and design specifications. If you were in the real world, what we would do with an ambiguous situation like this is you would go back to the stakeholders. Whoever told you to write this stupid program to begin with, and you'd say, what happens at 1? And then they'd realize, well, okay, we want you to do slight sensation then, right? That's going the back and forth. In fact, it's an entire area, it could be an entire course, of requirements elicitation, right? A fancy word there. Requirements gathering, right? How do you write correct requirements? How do you communicate with non-technical people on how to get requirements, et cetera, right? If you've ever seen, what is it? Not The Office. What's the other one with Peter? No, the movie. Office Space. There we go. Office Space, right? The guy that did requirements elicitation, right? Requirements gathering. He really actually didn't do anything. He just took it directly and then gave it to the engineers without, getting rid of these ambiguities. That's what he really should be doing, but he wasn't doing anything, right? So in this case, we'll go ahead and say that 1 is actually going to be a slight sensation. In that case, we don't want, say, less than or equal to, because if it's less than or equal to, we hit that 1, and that's going to have no effect, okay? So we want strictly less than. Else if m amps is between 1, so 1 is less than or equal to m amps, and m amps is less than, what was the other one? 5.2, oops, 5.2. Then we'll print out slight sensation. It's a slight buzzing sensation. Put a 9 volt to your tongue. I don't know, is that pain? 9 volt on tongue, I don't know what the impedance of the tongue would be, but you've done that before, right? It's crispy, there we go. So slight sensation. All right, we can continue. Right? Else if, ... But before I go on, is there a way that we could probably optimize this code a little bit, right? Or simplify this code. Right? Remember it's 5.2, so 62. The 5.2 is less than or equal to m amps, and m amps is less than 62. Printf, pain, or painful, or whatever. Voluntarily, I'll cut and paste this as a string, because there's a difference between pain and pain where you have muscle control and where you don't. Right? So is there a way that we could simplify these two statements that I just wrote? Remember that these are mutually exclusive. If I got down to this point where I'm checking for this, what do I know? It's not no effect, right? We know that it's already greater than 1. Why do I have to check for it again? Right? Okay, that's much simpler. If we've gotten to this point, we already know that it is greater than 1 and that it's greater than 5.2. So do I need that first check? Nope. Simpler code is better code. The KISS principle. Keep it simple. Right? Stupid, yeah. If you want to be mean to yourself, go ahead. Right? M amps. So I'm going to follow this pattern for the rest of it. M amps on 62 to 76, pain, loss of control. So 76, printf, pain, loss of control, and the line. Right, there you go. Else if M amps is less than, what was it? 90, severe pain, or printf, severe pain, and the line. There we go. And then else if it is less than, the last one is 500, then death.
Heart fibrillation.
Heart, all right. Not necessary, because you can defibrillate, right? All right. That looks like it's pretty good so far. Let's go ahead and compile it and at least make sure that there's no compiler errors. But what should I be doing? Do I need the math library, first of all?
No.
Nope. But what should I be doing always?
Wall.
Wall flag, and there are no warnings. We're good to go. A dot out, I didn't provide a value. That works. A dot out, 10. What would I expect here?
Pain.
Pain, involuntary, or voluntary muscle control retained, all right? What else should I test? That looks good. Ship it. All right, do something like 400. All right, I should expect heart fibrillation. Okay. Do we? I don't know. What if it's greater than 500? Is that good or bad? Bad. Certain death instead. Right? So what did I not put here?
You need another else statement.
An else statement. I could have done this, right? And now 600, anything above 90 or above is going to print out heart fibrillation. But a million amps, right? That's got to be something else. That's not just heart fibrillation. That's crispy toast or something, right? So I'll go ahead and restore that. What else should it be? Again, it was not specified. So you go back to your stakeholders and say, what else should happen if none of these apply? And they give you an answer and you implement that answer. Or you can just say, printf unknown, undefined.
Divide by 0.
Divide by 0, right? And this conforms to the specification, and you didn't have to go back to them, and if they sign the contract, you are completely within the bounds of the contract, and now you can go ahead and go back to them and say, okay, well, now it's going to be $500 an hour to fix it because you didn't provide me the correct specifications, right? So, well-established companies do this all the time. Right? They make sure that they have billable hours even after they deliver the product by delivering an incomplete product that nevertheless conforms to the contract that everybody signed. What does that tell you? Get a good lawyer, right? In fact, later on, there's a, I always have the optional reading and optional watching. Later on in the semester, I think towards the end, there's an excellent video called F You Pay Me, right? And it is this wonderful guy that goes through why you want a lawyer. Even if you're ever going to be doing any contracting work, you want at least a lawyer on retainer. And he goes through his process of what, he was not a coder, he ran a design firm. But he justifies why a lawyer pays for themselves in the first time that you use them, right? Because people can, violate contracts and not pay you. If you are going to be, doing contract work, there's a whole bunch of other things that you need to be aware. You need to become a lawyer yourself or get a lawyer. You need to be an accountant yourself or get an accountant, etc. Because that is a whole different world than if you're actually working for a company and just an employee. Right? Excellent, excellent YouTube video, watch it. Right? And then also watch the other lawyer videos on shut up. Don't say anything to any law enforcement agencies, ever. Right? They can never help you. Anyway, this is undefined. All right, let's go ahead and continue. Let's run this again, 600. Okay, undefined. Is that the only thing that I should be testing? What's another thing that I should test? All right, before I get to negative, let's test another corner case or a boundary case. What about 0? 0 should be no effect. Okay, that works. And then negative 10, or negative, any negative value. Slight sensation. Yeah, why? What happened?
It's
So-
less than 5.2.
Yeah, was this true? Nope. So it went on to the next one. Is negative 10 strictly less than 5.2? Yes. Remember, the first one that evaluates to true is the first one and only one that gets executed because of mutual exclusivity. So what do I want here? What's the solution here? Make another check. If m amps is less than 0, then I will printf, again, undefined. Undefined or maybe something else, I don't know. We already agreed that, can you have negative amps? No. Well, relative negative amps, but like you always have to, can you? Yeah, go ahead.
Suggestion, what if we just call absolute value for FABS?
You could, but then somebody gives you negative 10 amps, and you could, if you document that, that'll flip it to positive amps or something, non-negative amps, I should say. That if that's an expectation of the program, yes. If that was in your requirements, or if that was in your design specification, then yes. But otherwise, you're making an assumption that the user knows what they're doing, and that's never a good assumption, right? So you could go ahead and say that negative amps are not don't make sense. Don't make sense. I could take the absolute value and then spell it correctly, but whatever, right? In fact, let's do that. All right? Here you could go ahead and just echo this message and be done with it. And in fact, that's what this will fix it. Right? Negative amps don't make sense. I could blah, 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 blah. That'll take care of it, but let's go ahead and go with your idea. How would I code it? If it's negative, I could change it to positive, taking the absolute value, ABS, crossing my fingers here that this will work, of m amps. Okay, hold on to that thought here. I want to demonstrate that this will dunk up here. Anyway, absolute value, and then I could do the rest of this stuff here. Right? Good? All right. Let's test it out and see if it works. GCC. All right. Oh, I didn't have to link in the math library that time. I wonder why. I don't think it's in the math library. I think it's in the standard library. But in any case, we got it, right? A dot out, negative 10. Now this should be what? Flipped it to positive 10, so this should be a pain voluntary muscle control. All right, looks like it worked. Negative 10.5. Same, but for the wrong reasons. Let's go ahead and change this so that printf %f milliamps is ... and the line, and then we'll print out what we actually read here, amps. All right, negative 10.5. So I should read in positive 10.5. M amps is, and then that slight pain. Do you see 10.5 there, though? What happened? It's an integer. Abs is for integers. It will take the absolute value of an integer and give you an integer. I took the absolute value of a double, which happens to truncate. 10.5 becomes 10, or negative 10 in this case. Then takes the absolute value. So the solution is, and I heard it before, something even better, something more fabulous. Fabs. What does that F stand for? Fabulous, yes, exactly. Floating point fabulous. There we go. 10.5 milliamps is pain, voluntary muscle control is retained. Okay? Excellent. Then what happens to a positive? Oh, okay, so you could do something like that, right? You could say m amps is equal to m amps times -1, right? Because we know that it's negative, right? But do I even need to check? What's taking the absolute, what if you take the absolute value of a positive number? Does it change it? Nope. 0? Change it? Nope. So I could eliminate that condition there altogether. I could even eliminate a line and simply just take the fabs all in one line. Right.
I'll make it one line if you want.
I could take out all the white space and make it one big giant line. Don't go that far though, right? Let me go ahead and take it back over here. I still like that a little bit better, right? Because it's signaling intent. I intended to read this double, and then I intended to take the absolute value function, and then I intended this other stuff, right? A readable code is a lot better than clever code, and getting by with, instead of 10 lines of code, you get by with 3 lines of code. Okay? All right. Anything else with this? Well,
We don't need
if I change this, then do I need this anymore?
no.
Nope. I could eliminate that. All right. No harm in leaving it, though. I'll go ahead and leave it. All right. Good. Any questions on conditionals at all? Linters, anything? All right. Or whoever Charles Delzio is, I have no idea. It was just an internet search. Right. Okay, then, in the last couple of minutes here, we'll preview what we're going to do next time. In 1 second here, let me render this and open it in a new window. All right. So we need a way to repeat code. If I've got a line of code that I want to act on one piece of data and a second piece of data and a third piece of data and a fourth piece of data, but it's all the exact same code, then I don't want to cut, paste, cut, paste, cut, paste 4 times. First of all, that hard codes it to only be 4 times. What if it's sometimes 5 pieces of data, or 10 pieces of data, or n pieces of data, where n is some variable, right? And also, cutting and pasting code generally is bad. What you want is you want a way to repeat code. Repeat this code for the first piece of data. Repeat this code for the second piece of data, ... right? Or while some condition continues to be true or false or whatever, then repeat this code over here until it becomes false, and then stop and move on. Right? A loop, just like a conditional, is an interruption of the normal sequence of control. A, B, C, D, E, right? It goes A, and then repeat A, repeat A, repeat A, until some condition is met, and then you continue with normal sequential control flow. There are 4 basic elements to any loop, right? You have to have a starting place. That's an initialization step, right? If you're going to start running, which I'm dressed to run today. By the way, we on UNL campus, we have a run with faculty. If you're interested for the UNO version, we can do a UNO version. We usually just do a 5K. We could set that up in the afternoon. Anybody interested in that? Anybody run? All right, 1, 2, 3, okay. All right, well, I was going to do a 10K if you wanted to run out with me right now. But anyway, you have to start from someplace, right? I'm going to start out right here at the front of PKI. I have a continuation condition. I'm going to continue running until I've hit 5K, and then I'm going to loop back, right? And while it's 1, 2, 3, right? It hasn't met that condition yet. Only when I hit 5 am I going to come back. I have an increment, right? For every step, I am working towards that terminating condition. And then finally, you have a loop body, what you're actually doing in the loop. And what I'm doing in the loop is I'm just running, right? So you have an initialization, a starting point. You have a continuation condition, or alternatively, the flip of that is the termination condition. When do you stop this loop, right? If you don't stop this loop, what happens? If I don't stop this loop and I just keep running, what's going to happen? Heart fibrillation eventually. But I'll pass out. If I had superhuman strength, though, I would just continue going on forever, infinitely. That's an infinite loop, right? So you need a way to work towards the progress of, make progress towards that termination condition. And then, of course, the loop body of what you do. There are 2 types of loops that we'll get into next time, but I'll show them to you here. These are basic loops that count to 10. You have a for loop, and guess what? It uses the keyword for. And then you run for some variable. I'll start at 1 here. That's your initialization condition. You start at I equals 1. While I is less than or equal to 10, you continue this loop. And then you make progress towards that termination condition by adding 1 on each iteration of this loop. This is that idiomatic for loop, right? You'll see these all over the place, right? Actually, you start at 0 and then go up to, but not including 10. But in this case, I wanted to print 1 to 10. So I'll print %d, end of line, I. What is this going to print? It starts at 1, right? And 1 is less than or equal to 10, so it prints 1. Then I++ will increment it to 2. It'll print 2, it'll print 3, 4, 5, 6, 7, 8, 9. 10 is less than or equal to 10, so it prints 10. And then it goes up to, I've run out of fingers, so 11. Is 11 less than or equal to 10? Nope, so that's when the loop stops. An equivalent loop would be a while loop. Int I starting at 1, while I is less than or equal to 10, print, and then I'm just going to steal this, print I out, and then increment it by 1. These two loops do exactly the same thing. Sometimes you want to use for loops, sometimes you want to use while loops. We'll talk all about that on Thursday, though. Questions? All right, that's your preview. I'll see you on Thursday.